have it Thursday, but we definitely move it to Monday. And that would mean that, we'd have Tuesday review for the final. So, we'll see how it goes this week, you know, and, I'll talk to you more about it tomorrow and Wednesday. We definitely have that test on Monday though. Hey, good evening, everyone. Hey, so today we're gonna, work in sections 5.2 and 5.3. This involves these definite integrals that we're working on. I put two things on the board. I mean, if you want to copy, you can. There's more wording from the textbook. I want to tell you what pages I got these from. This one right here, I didn't finish the whole the theorem, but this is called the Fundamental Theorem of Calculus Part 1. So I'm going to write FTC Part 1. And then this is called the Fundamental Theorem of Calculus Part 2. Okay? This was the last thing we did last class. But this gets stated in section 5.3 of the textbook. The Fundamental Theorem of Calculus Part 1, Part 2. I didn't put all the wording down though. And you can definitely see all the writing, which is on page 388 and what's the next page? Page 391. They include this wording. If f is continuous on the interval, closed interval a to b, then the function g is defined by this. So I want to point that out. If you want to put all that extra wording, here's the gist of it. We're saying, okay, as long as that function g is, you know, continuous on that interval a to b. Same thing with part 2. You'll see that written on page 391. They start out, if f is continuous on the closed interval a to b, and you get part 2's there.
Now, on part 1, g prime of x equals what?
Yeah, so I left it blank. And I bet you can come up with it.
F of x?
Yeah, so what do you think? If this integral, as we noticed, was finding the antiderivative, what would happen if we took the derivative of that? That should put us right back to what?
Original equation.
F of x. And I'll make sure to demonstrate that to you. So I wanted to leave that blank. I want you just to let everyone think about that. You go, yeah, what would that equal? And this is the Fundamental Theorem of Calculus Part 1. If g of x is this integral of f of t dt from a to some x, well then the derivative of g should just be f of x.
Oh.
So we go, all right, it's like almost like removing that integral. It's similar to this concept, right? You take a number like 3, you square it, you get what? 9, then you take the square root of 9, you come back to a what?
3.
3. It's very similar to that concept, and we'll do an example to better understand this. So right now you're looking at this going, I'm not making sense. Why is g prime just being this f of x? We'll do an example so you can actually see it. Okay, you can actually view it and understand a function that does that. And then this is just saying, on a closed interval a to b, all we have to do is take, this is a capital letter f of b minus capital letter of f of a, where big F represents the antiderivative of lowercase f. They use that notation a lot in calculus. And the uppercase, big F, is considered the integral of lowercase f. So we'll look at an example like that as well. Okay? So I think I'll start with something like this. Now keep in mind there is some extra wording, right? If the function is what? Continuous. Because what if the function wasn't continuous? What if it had holes and things like that, right? What if it was broken? All right. That stuff doesn't apply. As long as f was a continuous function. Same thing here. So here's an example. How about this? Just this function. I just want you to think about it. And then I'll write an expression like that. Or excuse me. Then how about 2x? We'll start with f of x equal to a 2x. Do you remember how to do the integral then?
Yeah,
What would you get?
x squared.
Yes, if you did antiderivative, you'd say leave the 2 in front. X squared over
2.
2? Sound agree? Cool. So we're going to do a problem like that. But if we do all this work and then we come back and take the derivative, then we should come back and do a full circle and come back to a what? Like a 2x. Does that make sense? So let's try something like that. Keep in mind the way this is written, see this letter A in here? That's any constant. That would be any constant that's, you know, where x is between A and some value B. Where B can anywhere down the line. B can be some value way down the line somewhere. You go, where's B in this expression? You know, off to the side, keep in mind, they said, that when if f was continuous on the interval A to B. I just don't want to make you, you know, include all that writing because you will see that right in the textbook. So how about this? All right, I'm going to call this g of x. A can be any value, right? Okay, I'm going to get a 1. That's x. And I'm going to make f of t 2t. dt. All right? Hey, run the function y equal to 2t, similar to y equal to 2x. Isn't that function continuous? Straight line, right? Okay, good. It's a straight line. Well, if we did the antiderivative of 2t, what would we get again?
T squared.
2t squared over the 2,
2, yep.
right? These 2's cancel? And don't I have to put plus constant?
Not on the.
Plus C.
Good.
No, but not on the.
Very good. He says they're going to cancel out anyway.
Yeah,
Very good. So I'll put it, but that plus c will what?
cancel.
Will go away, won't it? Right?
Where does it cancel out with?
Yep. It always cancels out on the definite integral. And we got this x and we got this 1. So I'm going to go over here and put an x, and I'm going to put a 1. But you're right. He goes, you don't have to put that plus c. You're going to get a c minus c. They're going to subtract to be 0. Cool. Now, I got to substitute x in for what letter?
T.
T. Then I have to substitute 1 in for letter
T.
T. And then I'll subtract these. Okay?
Okay.
All right, let's do it. Put an x in here, you get what?
X squared plus C.
All right, so I substitute the x, check it off. Then subtraction,
1 square minus C.
substitute
Plus
1 in
one.
there.
C.
Just like we expected, everyone, these c's are just going to what?
Cancel out.
Yeah, they're going to cancel. So what do we get for this expression?
X
We
square,
get g of x is equal to what?
X square minus 1.
All right. Now let's see if this is true. Okay, I'm going to write the word okay. And we get x squared minus 1. So, okay, what's g prime of x?
2x.
Did we do full circle?
Yep.
Let me just everyone look. It's like, oh yeah, we get it. We get this concept, you know, this idea. 2t, it became this t squared. Put these in here. Now if we went back and took the derivative, we come back to a what? A 2t.
The 1 squared plus c, and minus c that we put there, where did you get that from?
That was from substituting this one, that would be called the lower limit, into this expression for t. So really, see this x and this 1 here? If you want to, Josephine, right here next to these, you could say, because this is in terms of t, we're saying t is equal to an x, t is equal to a 1, and you could substitute both of those into the t value. And we always take the subtraction. We subtract them.
Now, for the test, for definite intervals, is it okay if you don't include the c? In
Oh, heck yeah. Please don't. Because you're telling me, hey, if it's a definite integral, what happens every time?
They can't.
So it's just going to go out anyway. Every time, right? Very good. So every time you have a definite integral, when he's talking about you got this integral symbol and there's something here and there's something there, he's saying you don't have to put plus c. Right? But if there's nothing here, we'll put plus c.
What happens when x is at the bottom?
Ah, great question. We'll talk about that. That's a great question. Make sure I answer that.
Isn't
I love that. I'll read and we'll talk about what to do.
Isn't what's on the bottom is the root thing?
Yeah, but you know what was neat about this problem? This lower number was what? 1? Okay? We got this constant, 1, it could be a 5, it could have been a 7. when we substitute it, we just got a number over here. But what's the derivative of any constant? What's the derivative of any constant? Zero. So that's why this will always be equal to that. But it's in terms of x. Does that make sense? So when you follow all that stuff? Cool. I'm gonna make sure to do your example. And what I'm gonna do a big wall here. So this was kind of giving us a sense of part one. Let's look at part two. All right, how about this? I want you to find this. Go from 0 to 4 of 2t dt. So there's a definite integral. All right, we don't want the plus c's, right? We're not going to do it. But what is this finding? And remember we were doing the Riemann sums? Wasn't it rectangles?
Mm-hmm.
So first of all, could you tell me about this function right here? Isn't that a straight line?
Yep.
What's the slope?
2.
So I'm going to rise 2, run 1. But how far do I got to go up to? I got to go from x equals, or these are t's. Let me put t here. I got to go from t equals 0
to 4.
all the way out to t equal to 4. So I would like it if you just take a second to draw an image with this. Draw the function. What would it do? How high would this get it?
8.
1, 2, 3, 4, 5, 6, 7, 8. All right. Right there. Let me just get this thing up here. There we go. All right. Riemann sums dealt with those area of those rectangles, correct? So when we do this, this should find the exact area of that what? That triangle. And I think when we're done, we should check it. Who remembers the area of a triangle in geometry?
Half base it into height.
Half base times height. Okay, so when we're done, we're going to check it. Make sure this works out right? That's why I didn't want to do a curve at first, so it's something you could really check. But after that, we could do it with any function, as long as it's continuous. As long as it's continuous. All right, what's the integral antiderivative of 2t?
T squared.
Divided by 2.
Good, the 2 and the 2, and these just do what?
Cancels out 2.
All right, take those out. Now I'm going to go over here, definite integral, t equals 4, t equals 0. And if you want, everyone, if you're getting used to this, you might write, this is where I'm going to let t equals 4, the upper limit. This is t equal to 0, the lower limit. And I'm going to substitute these in here.
You substitute the 4 and the 0 in for t, right?
That's right. And you always do not an addition, but a what? Subtraction. So what it'll do, it'll accumulate the area to 4, and then it would subtract out how far you accumulated to. So let's just see what we get. I put 4 in there, I get what?
16.
16. I put a minus. Then we substitute the
0.
and the answer I'm getting is 16. What's the area of that triangle? Half base height.
So base is 4.
Base is 4, height is?
8.
And then what's half of base
32.
4 times height 8?
16.
16. Isn't that cool? I'm going to change one little thing. And I'm going to answer your good question about, hey, what if, he goes, what if that x was on the bottom, right? It's going to be easy too. You'll like it. Hey, let's change one thing. Ready?
So he's asking like the x is on the lower limit.
Yeah.
Okay.
He goes, what if, and he's like, what if this was x here, and then I would put a constant up here?
Okay.
And we'll go, oh, we'll come up with something real quick. All right. What if this was just 1? How would that change?
So
Then it
4
wouldn't be
squared,
16,
12.
it'd be like,
And think about it. What would it find in this image? It would accumulate the area to 4, and then you'd have to subtract out the area from 0 to what?
1.
So what would that represent? The area under this line, between this line and the x-axis, but don't I have to blank this right here?
Mm-hmm.
So when look at this, this is what this is finding. It'll find that area. That's a trapezoid now. So I didn't want you to think it's always 0. Sometimes it's a 1 there. So I'll change this to 1. Now we're subtracting out what?
1.
1 squared. So what's 16 minus 1 now?
12.
15?
No, 15. Yeah. Mhm.
So what's the area of that region right there?
So base is 3. 8 times 3 is 12. No, 8 and 3 is 24 divided by 2.
Good.
So that's 12, right?
Yep, and I think a great way to think of this, Owen, if you wanted to check this, you go, how could I check to make sure we did this right? It's the idea of what? The area of the whole triangle would be 16, and you'd have to just subtract out the area of that little blank triangle now. Because that's not part of the image. What's the area of that little blank triangle? What's 1 times 2 and then take half of that?
2,
One.
1, so you're going, oh, 16, subtract the area in there, gives you the entire area of 15 in that image. Does that make sense? That's why we're subtracting. I want you to understand, why are we subtracting? Because you're going to subtract this out. You take the whole area from 0 to 4, subtract out the area from 0 to 1, you'll be left with that region.
It's also, the height will be 6, not 8.
Yeah, so right here, that height would be 2, that would be 8. You could do, if you wanted to, you could do area of trapezoid.
Huh. So what is the total height? That means, like, what will be the total height? 2 and, oh, you have to do two heights, right?
Yeah. I was thinking this, like just to check this,
Uh-huh.
Art, I was thinking we could just say, oh, think about this. This is like the area of the triangle from 0 to 4.
Yeah.
Alright. Subtract out the area of the triangle what?
0 to 1.
0 to 1. In that image. And we're getting 16 minus the 1, which is what?
15, okay.
But if you wanted to check it another way, you could go, well, what's the area? That's a trapezoid, isn't it?
Uh-huh.
When a trapezoid is a 4-sided quadrilateral where there's 2 sides parallel, and you gotta do half the base times some of the.
So, yeah.
So if you think about the heights are on the side, aren't they?
Yeah.
So like half the. So there's base 1, that would be base 2, and the height there would be what, 3?
3, yeah.
If anybody wanted to, and when the area of a trapezoid is 1/2, right? The height of the trapezoid times the sum of the bases. The only thing is when you look at that, you gotta think of the height being like on the side, because the big faces have to be parallel to each other. Anyone good with all that? Hey, cool. So I'm gonna erase this. Everyone, thanks for bearing with me on that. I wanted to make sure you got a sense of these two things, because we were hitting them all day today. Fundamental Theorem in Calculus, Part 1. Fundamental Theorem in Calculus, Part 2. Just call them FTC. And Friday, I'm going to go to your question. All right, so I'll make it a different constant. How about 3 this time? Whoops. This was an x, this was a 3. 2t dt, and let's try this again. According to Part 1, Fundamental Theorem of Calculus, what would the derivative of x have to equal?
2.
No matter what, according to the Fundamental Theorem of Calculus, Part 1, it will just equal what?
2.
This right here. This function. But you got to substitute what variable for t?
X.
Sound agree? Is that not good enough? Alright, let's make something crazy. Let's make something like just bizarre. G of x equals, this time we'll go to 5. You all know this constant's not matter in this expression here. Here's the variable x. Cube root t to the 5th minus 7 dt. And you and I have to find g prime of x. Well, according to the Fundamental Theorem of Calculus, right?
Mm-hmm.
Let me just make sure that function's continuous. Yeah, it's cube root. We're okay. What would this come out to be? Cube root minus 7 to the 5th power. The only thing is, what variable do I have to use?
X.
Because it's in terms of x. And if you ever get confused, why is this happening? I want you to go back to our example. When you saw it just come back to be that 2t, remember? And then we got the 2x at the end. Right? We went through it. Now, your question. Now, what if this switches around? So that means the whole thing gets reflected on the x-axis. Whereas the property of integrals, and it says this. Can you switch things like this? Oh yeah. But because of symmetry, Wah, wah. As long as the function's continuous, right? This property holds. So I can do that, and we can switch it, but what symbol do you have to put down?
Negative.
Negative.
Oh, so you're doing a lower bound and upper
There you
bound
go.
switch, okay.
That's what's happening. It's like the whole thing just got flipped over. It's that simple. So hey, let's do one. I'm gonna make up an expression. I'm gonna put the variable down here this time, okay? I'm gonna put the number up here. You can make up any function here for us, and we'll write the answer. And then, oh, then we can put a negative in front of it. So we'll try this one. All right, everyone here star this, because look, he came up with this one, it was good. We're putting the variable here. All right, that's a 1. Now make up some function, anything.
19.
All right, 19. Oh, that's a 9. Let me make sure it doesn't look like a G or anything. 9t dt. All right, what would g prime of x have to equal? Well,
9x.
the first thing I have to do is really, it's going to be this but negative. It's going to be a 9x but negative.
Why is it
But
negative?
because it's property, the first thing I should do is apply it and just say, by this property, it's equal to negative, and then I get to do what? Switch them around. So now we know that the answer with g prime of x, it'll just be negative, constant in front, and then just what? 9x. The biggest error, students sometimes they go, why is x, why, this is t, how's it become an x? It's because doesn't that x get substituted?
Mm-hmm.
That's why. That throws students off sometimes. They're like, I don't understand why it's not t in the end. It's because x actually got substituted. Why didn't the 1 hang around? Because you took the derivative of a constant, it turns into 0. Isn't that cool? Alright. So the answer to this one? Negative 9 of x.
Would you switch the x and the 1? X was on the top, or on the bottom.
Yep, we switched them over, but we had to put a what?
Why
negative
did you
there.
make it a negative again?
Oh, because of this property.
How do you know when you're supposed to use that?
When the variable is on the bottom. Good deal.
I'm having some hard trouble understanding the difference between the two. So part 1 and part 2.
Okay.
When do you use?
Great question. I'm going to give you a couple examples. Most of the time, you're just going to use this. You're not going to see many of those. But what we're trying to emphasize with part 1 of the fundamental theorem of calculus, we're trying to emphasize how the derivative of this will just be what? Yeah, that derivative of this expression in terms of x. You know what I mean? Like g of x took the integral, and then you come back to this. So I'm going to pick a problem out of the book so you get a sense of this one. And when this is like page 394. And don't worry, I'm going to come back to 5.2. I'll come back to 5.2, but this is like page 394, number 3. That's one of the practice problems I saw. Okay? So I'm going to make something up. I'm going to make some image. I was playing around with this. Alright. And when I got to make something that I know you know how to find area under, so I'm going to use straight lines, okay? Can we find area of triangles and things of that sort? Right, without calculus? So here we go. One, 2, 3, 4, 5, 6. How did I make this? I'm going to go up to 5. 1, 2, 3, 4, 5. 1, 2, 3. All right, I'm going to have this graph start here at 3. At 1, it's going to get to 5. At 2, it's going to get back to 3. At 4, it got to 0. This graph's going to go like this. Yep. 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 1, 2, 3, 4, 5, 6. I'm gonna call this T. All right. I'm gonna call this the graph of F. I mean, that's a function, right? And I'm gonna write this. Let g of x be defined as this. So I'm making this up. This is like that problem. And Rod, this is so you can better understand this. Like when do I use this? When do I need to do this? It would be a problem if they just told you to find a derivative. You know, just put that there, right? But here's this problem. Most of these start at 0. I don't like that, so on purpose, I'm going to start this thing at 1. Okay? So that's the number 1. I'm going to put the variable t right here. And I'm going to put f of t dt. Okay? Now everyone, don't integrals deal with area? Okay. So we're going to start finding areas. That's why I use straight lines. This better help you better understand fundamental theorem of calculus part 1. And this is like that problem out of the book. So what do I want you to find? Everyone, I want you to find the v-values. Now notice I started at what number? 1. I did that on purpose. The textbook always starts at 0, and sometimes students get to a test and they assume you just start at 0. You know, your eyes just start right at the origin. Well, this thing's starting at 1. So I want us to find these. And let's just call this letter A. Everyone, letter A, I want you to find g of 1. Then I want you to find g of 2. Then I want you to find g of 4. And finally, I want you to find g of 6. Okay? Now, what is g? G is defined as what? G of x is defined as the function that's the integral from lowercase, lower limit 1 to variable t of f of t. Now, if this looks all confusing, don't let it be confusing. Everyone go back to Algebra 1 class. What if I said, oh, g of x equaled 5x plus 2, and I asked you to find g of 2, you all know what you do. Where do you substitute the 2?
X.
For x. Did everyone hear that? Go back down and go, what did you do? You substitute 2 for what variable? For an x, back in Algebra 2, correct? Okay, so I want you to do the same thing here. I need you to find g of 1. Then you say, I'm going to substitute what number for x?
1.
A 1. So that means going to this whole right side, and I want you to find, oh, let me make that an x, I apologize. That would have been all messed up, I apologize. We're going to substitute 1 for the x value in that right side of the image. All right. So I want to find g of 1.
Can you have an integral with the same number on both sides?
Yep. So this is what I'm getting. Now, what do you think this answer is going to be? Find the area underneath this function from
0.
1 to 1.
0.
So in one of the properties of integrals, what's the integral going to be when you go from the same number to the same number here? Every time, right? Because you can find in the area underneath from here to here, you're not going anywhere, so what will be?
0.
0. So what's g of 1 equal to? You and I don't see g, do we? What picture are we seeing? What image?
F.
F. But I'll tell you what, when we're done, you and I can build g. Isn't that cool? We can actually build the g function. We know one number so far. What's g of 1?
0.
0. So hey, I mean, just as we go through this course, when I make up some function later on and I go from 5 to 5 of x cubed dx, could you tell me what the answer is going to be?
0.
0, right? We're saying if these are the same, you're always going to get what?
0.
0. Everyone so far so good? Now notice, we said, yeah, if you're plugging in a 1, you just plugged in a what right here? 1. Well, let's go to this. Now take it slow. What does g of 2 mean? It means go into that equation on the right side and substitute what for that x?
2.
2. F of t dt. And you and I say, well, integral's fine, we know by Riemann sums, area underneath the function, between the function and the x-axis. True? Right, built all those infinite amount of rectangles. All right, let's get the area from 1 to 2. Now, I put straight lines on purpose so you and I can find the area. So, what are we trying to find?
1 to 2.
Oh, we gotta find this area. Now, we gotta use geometry, okay? We're gonna have to use geometry, we gotta find that area. But I know, we all know area of rectangle, length times what? Width. And we all know how to get area of a triangle. Half base height. Somebody might go, hey, that's a trapezoid, right? But you might not mess with it. Can't you just get the area of the rectangle, the area of the triangle, and add them together? Yeah, most students do that. Good. So let's find this area right here, because that's what it's going to be. We're trying to say, find the area from 1 to 2. Is it going to be positive? Yes, because it's above the what? X-axis. You and I are going to be very careful when this function dips below the what? X-axis. You go, why? Because then we know y values go negative. And if that's the original definition, that means y, so we're just going to be careful. But right now, everything's above the x-axis, true?
Mhm.
So let's write in here the area of this. What's the area of this whole region right here? That rectangle.
1 times 3.
That's an area of 3, length times width, 3.
Uh-huh.
Cool. Now you can do a half base height there.
1.5.
So 2.
So half of 1 times, what's that height
2.
there?
2.
All right, I'm just going to draw an arrow like this, and you got to do half the base length, 1, times the height, 2.
2.
What's a half of 1 times 2? 1. Everyone agree?
Uh-huh.
Let me just make sure. Is the area of that little triangle 1? Sometimes it gets confusing. You're like, wait, and you're like, oh yeah, what's that length of that base? 1, what was the length of that height there? 2, all right, what's 1/2 of 1 times 2? Everyone so far so good?
Uh-huh.
Cool.
We found the 3, but just finding the height.
Oh, do you agree? I'm saying the area from here up to there is 3. And all I did was area of the rectangle. Thanks. Area of the rectangle, length times width. And you go, all right, the width, this length is 3, this width is 1. True? All right. Now, you got to sum those areas. What is the integral from 1 to 2, the definite integral? What's that area?
4.
Let me make sure. Is everyone okay with this? Yeah? Cool. So g of 1 was 0. What's g of 2? 4.
4.
Cool. And everyone, we don't see the image of g, do we? The function.
Wait, how did you get G of 2 again? I lost you.
We plugged in 2 right here,
Okay.
and then we got the areas.
Areas, oh, okay, up to 2. Okay.
There you go. Good job. Now everyone, I want you to get g of 4. Now take it slow. What does that mean? Substitute 4 where?
Into
Here, and it replaces that with a what?
with the
4. Good, so I'm going to write it. I'm going to put a big wall. That means do the integral from 1 to what?
4.
4. And we got to accumulate the entire area from 1 to 4. But why did I use straight lines? Because we know how to find the area of triangles and rectangles, right? Do you all agree if I made some goofy curve, you'd be sitting here going, we don't know how to get the area of that curve?
Professor,
Yeah.
we don't need to do 1 to 4. We already did 1 to 2, so you can just do 2 to 4 and add it up, right?
Brilliant. Everyone agree? Do you all agree with them? You say, listen, save some time here. If we now got to get the area from 1 to 4, we already found the area from 1 to what?
2.
2. Let's keep that, and then we'll add it to the area that's what? 2 to 4.
Yeah.
So it's a good idea. Leave this here. Don't erase that.
So 4 and then.
And then is that a triangle or rectangle?
Triangle.
So let me, I'll just draw an area. You got to do half base height. Now be careful. What's that base length?
2.
2.
Height is 3.
Height is
3.
3.
It's 3.
I know sometimes everyone in the problems in the book, you get the 0.5s to come up, right? But what's half of 2 times 3?
3.
Now, all right, I like your logic. I think people agree with you. Add all that up. How much is it coming out to be?
3 plus 3.
Does that one agree? Now, can you get a sense of what's going on with function g? It keeps going up, doesn't it? Look, we don't see g, do we? But the function g, continuous function, is what? It's increasing, isn't it? All right, okay.
Now
So far, so good? Like some of you might have go off to the side and make an image of g. I'm like, let me see what G's doing, look. Just off the, look, here's G. At least we got a few points. What was going on at 1? 0. What was going on at 2? 1, 2, 3, 4. And what was going on at 4? 7. Okay. Just an idea, right? Maybe it curves another way, but this is what's going on. Going to here, and it's going to here, and it's going to here. Now, I want you to find one more thing.
G of 6.
Be careful. You bet we're going to use all that information to get this. But now, this function has gone underneath the what?
Axis.
X-axis. We'll find that area, but we're going to assign a negative value to it.
What's the y value?
The y value right there, yeah, I better make that
Negative
clear. Thanks, Kel. How about we make that, I didn't make this so nice.
Negative
So
2.
won't we be?
How about negative 3?
Negative 3.
Yeah, I'm gonna make that go down to everyone in this image. This is gonna line up to the value right there, that's gonna be g equal to negative 3.
So won't we be finding the area of the entire triangle instead?
We're gonna get that area right there,
Or are you gonna subtract?
we're gonna find it, and we're gonna subtract it from this last value.
So first you're gonna find the area of the entire thing and then
Yep.
subtract the
There you go.
area between 5 and 6.
Very good.
Or
Now,
four-
what's this
4 and
area?
6, I think.
So
What's
the
that area right
base
there?
is 2
Half base,
and height is negative 3.
and the height is negative 3. See, that's the y value.
Yeah.
You go, why are we making this negative? This is the reason why. That's why I wanted to leave this up here today. This all came from this. And when see right there, that says f of x. And f of x takes on negative values when it's underneath the what? X-axis. So when we do this, we're saying 1/2 2 times,
Negative 3.
and most students just go, I'll get the area of that triangle and put a negative value to it, right? So now, to get this,
It'll be
I'm going to take the previous answer of all the sum from 1 to 4, which was how much?
7,
7, but then I'm going to have to subtract out
3.
this 3 we're getting.
Okay.
Aha. So when you see why I'm subtracting 3? Because of the what?
Yeah, the area.
If it goes underneath that x-axis, negative, right?
Isn't it because that's the area?
Yep.
Yeah.
So now 7 minus 3 is?
4.
4.
Alright.
All right, so hey, come on over. We were thinking about G, right? What happened at, what number? What went on at 6?
It's 0.
It went down. Became
Went back down to a what?
negative 4.
Well, it didn't go negative, but what was its value at 6?
4.
Oh,
Right? Hey, G1 it was 0. And 2 got up to 4. And 4 got up to how high? Got up to 7. Then back at G at 6, G got to what value? 4. True? So,
Oh,
Here's
and
my
then
next
when we
question.
go back.
part B. And because this is what they do in this problem. And letter B, find the absolute max of G on the closed interval 1 to 6. And I want you to find the absolute maximum value of G on the closed interval 1 to 6.
At x equals to 4.
We have enough information to get this. What's the highest it reaches? Alright? So I'm going to write out a sentence. The absolute max of G on this interval occurs at x equal to, let's fill in a blank right there, and is, let's fill in this blank. So from 1 to 6, what's the highest value that G ever took on?
7.
That's why I was making this image. I think you can see it. What was the highest it got up to? Got up to what?
7.
7. And when did it occur? At what x value? At x equal to 4. And it reached how much? 7. Someone agree? Now, guess what?
We have to find the derivative.
Do you remember the last test? It was on the second page. I gave you a derivative graph,
Mm-hmm.
and you had to come up with the original. You had to come up with all these questions about the derivative.
Mm-hmm.
Fundamental theorem of calculus. What's g prime of x equal to? F. This is g prime. This
Oh, yeah,
is g
yeah.
prime. Now when I know it says f, I was building g over here, but this is also what?
G prime.
G
G, would you make a note? Just go, aha, this is g prime. That's what's going on here. And do you remember the connection? Look. Think about the last test. Remember when you looked at something that went like this? That meant it was a max value of what? Of g. Do you remember this?
Mm-hmm.
That's why I wanted you to see this connection. This is the function f, right? And here you and I, we just answered this question. We found all these g values. We kind of built g from those values. The max occurred at 4, and what happened on this graph? It was going where? Because this is really, what graph? This is g prime. And when g prime is 0, that means it's a what? An extreme value, max or min, right?
Ah,
So the graph you built up there to the left, that's G prime.
Nope, I want to be clear. This would be just g. This would be g.
And that's
That guy would be g prime.
okay.
And we go, oh, g prime is equivalent to f. We're looking at this going, oh yeah, fundamental theorem of calculus, g prime would just be f without that integral. Do you see the connection?
Yeah, I got it.
Does everyone see this connection? That's why I wanted to sell you on that, because I wanted you to see this, what's going on with this integral. I know, because you're like, well, what is this? Where is this needed? We're able to go, aha, okay, I get it now. Right here, that would be g prime, graph went what? Positive slope to what?
negative.
Negative slope, we're like, yep, we can see it. Is that one following?
Oh, so from G prime we're constructing G graph.
That's right.
So, but that is not only absolute max, there's also local max too. The-
Yep, it would be a local max too, very good. We were able to say absolute max because notice what I did, I closed off the what?
Interval.
The interval. So that's why I put absolute max on there. Now, and when I'm going to put a part C down, I want to show you what a lot of students put for the answer. Josephine, I don't want you to make this little error. Takes on a -1. Here it comes. This is the killer question. Then tell me, what is this equal to? You got to fill in this blank. You got to fill in this blank. I'm going to screw it up, and I want you to correct me. Ready? Because you're like, I know the fundamental theorem of calculus. There's g of x, right?
Uh,
I get this a lot. You ready? They're close, but they say that. They almost had it. They missed one of the variables.
f of x.
It's got to be what letter?
Yeah.
X. People go, why is it t? It's got to be x, because it's the idea of this is what? Getting substituted. Now I'll put a smiley face. There we go. It's g prime of x is what? F of x. There it is. There it is. G prime of x is f of x. Isn't that cool? But Bellratch is not a t, right? Because this is in terms of what?
X.
The variable x, and that's getting substituted every time. Cool. So hey, I know when you go, when would you really got to think about this? It'd be for this problem, or the other example where I'll show you again, where if they had something, I'll put it really small here. If they said g of x equals, I'll put a 0, x, and they go x to the 5th power, or excuse me, t to the 5th power dt, and then they ask you for g prime. You don't have to go do the integral and take the derivative. You know g prime of x will just be this one. That right there, and substitute what variable for t. You go, why? Because of fun FTC part 1. Cool? But the rest of the class, we're going to play with this. Now everyone, for practice, would you try number 3 on page 394? I put it as a practice problem. The author started at 0. Okay? I could have started this at 0. What would have happened? We would have got the area where?
From 0.
Yeah, we would have started getting all that area. Does that make sense? If I started this at 0, we would have got this area in there too. Everyone okay with that?
Mhm.
Yeah? Alright. Hey, and most importantly, don't forget, when it goes underneath, what do we gotta do? Subtract out, right?
If you started at 0, all those areas would change.
You were right. That number would change, that number would change, this number would change, and that number would change, because If you start at 0, what are we including?
The
What's-
first section.
Oh, you're good, you're adding this amount to every one of those values. This would have probably went up to what? If we got that area in there, we could probably find it real quick. If you wanted to do it.
So that's
I think we should do it right for a race. What's that area right there?
So that,
Alright, that's 3. Now, let's see that little triangle.
1.
Yeah, half of 1 times 2 is 1. So, how would, if I do this, ready everyone? This is Josephine's point, that's good. If that was 0, and this was 0, and this was 0, and this was 0, and this right here was also 0, these would all change. This one would be
3 times.
3 plus 1 is
3,
4. Do you
Four,
agree
yeah.
the area underneath from 0 to 1 is
3.
4? Now, everyone sum the area from 0 to 2. Is that 8? Everyone here, add all those up. 3 plus 6 plus 1 plus 1, 8. Add this one up. What's that go up to? 11? And then lastly, you gotta take the 11 and subtract out to what? 3. So everything got shifted up by how much?
1.
That's what happened. Right? Each one of them. 4, 4, 4, 4. Can I raise? Yeah? Alright. Man, I think you got it. You got it. Well, let's have some fun. Let's have some fun now. So that's 5-3 stuff, but now I'm gonna bring in the F5-2 stuff. We're gonna do some definite integrals, okay? Here's my first one. Now, I am hoping we're gonna do this 2 ways, okay? 2 ways. One way is, let's find the antiderivative. We're gonna substitute what? 2 pi and 0, and we're gonna get the answer, right? And we always do a subtraction, true?
Mm-hmm.
But I also want you to think of the image. And sometimes don't forget about what you're trying to find. Who knows about the function sine of x?
From 0 to goes up, or 0 to 1.
Yeah, Josephine, you know the function sine of x, right? It does the little what? Goes up and goes down, right? I said, hey, know that trig sheet? Everyone, you only gotta know those basic functions. Sine of x, cosine of x. This function did what? At pi, it got back down to 0, right? And then at 2 pi, it came back like this. Someone agree?
Mm-hmm.
Aren't these areas symmetrical?
Mm-hmm.
Now don't shout out the answer. A lot of people already know the answer to this question based off this concept we've been talking about. A lot of people in class go, I know the answer. Because we're going to do what? We're going to take this area, positive value, and then we're going to subtract out this one area. I mean, who already knows the answer to this problem because of symmetry? Look at the hands. That's more than half the class. What is it? The answer is what? And I love that. And when I love it, you're able to say, hey, listen, you can waste your time doing the math, but the answer's got to be what? 0, because we have knowledge of this function. It's an odd function, but we know these areas have to be symmetrical.
Mm-hmm.
Positive minus this. But, can we check it? What should we get for our answer?
0.
All right, let's do it. Now, antiderivative cosine, oh, is it negative cos? Is it positive cos?
Negative, negative.
Every calc student mixes these up. We don't want to mix one up on a test, so SCS, CS. Which way are we going for integral?
Up.
Up. Right? All right, now we're going up for integral, right? Going up for integral. So the antiderivative sign is?
Negative cosine x.
Do I have to put the plus C, Belrage?
No, you
Good. Because these have numbers on them. It's a definite integral. Okay? I go off to the side and I put a little vertical wall, right? Go ahead.
Can you explain why you're not putting the plus C in?
Oh, because these have numbers on these limits right here. They're called the limits of integration. So, I could do a plus C, but what's going to happen, I want you to see why though, Josephine. If I put a plus C here, I'm going to substitute what in here? 2 pi for what value? I mean, for what variable, excuse me. I'm going to substitute 2 pi in for the x, then I'm going to substitute 0 in for the x, and I'm going to subtract them. I'm not substituting it into this constant c, and don't we always subtract? Right? Don't we always subtract? So what's going to happen? What's c minus c always going to be? A 0. So you don't have to put if it's a definite integral. So I just want to give you a quick example. On this problem, you don't have to put the plus c, but if I ask this, you can put this in your notes. I want to give you time to do this. If I asked you for that this question right here, evaluate. Now this is called an indefinite integral. Okay. Evaluate the indefinite integral. Oh. Josephine, I don't see anything here, right? So we're just going to have to put down the antiderivative. What's the antiderivative positive sign? And now I put the plus what?
C.
C. This is called a what? What kind of integral? A definite integral. So evaluate the definite integral. Aha! Definite values that we can actually find the area and accumulate the area. If the function goes underneath the x-axis, we're going to subtract that out area, correct? Does that make sense? So indefinite integrals, there's no limits here. We're just putting down the what? The antiderivative. Is that clear? So hey, when are we going to put plus c every time with these integral symbols? If there's no what here? There's no numbers. You don't see any numbers here.
Does that count if it's a variable as well, like if it was A and B?
If it's a variable and a number, then we don't have to put the plus c down.
The only time you put the plus C down is if there's no.
Just blank.
Okay.
Just blank. And you know what's even better, Josephine? What if you put down plus c 100% of the time? You still would be fine because what would happen anyway? The two c's would just what?
Cancel out.
Cancel out. Cool. Hey, so I'm going to do this. I don't have to put plus c. What number do I have to put in there?
2 pi.
2 pi.
Mm-hmm.
Now be careful, everyone. Is it a plus or a minus? Look. What's this say? I got to do what?
Minus.
A minus. It like accumulates area and then it subtracts out the accumulation of the next area. So I have to do a minus. Then you have to put a negative. And then a cosine of what?
0.
So far so good? Yeah? What's a minus times a minus?
Plus.
Negative times a negative is a plus. Alright. Now we all expect this answer should be 0, right? Who knows a cosine of 2 pi?
1.
That's a 1. Who knows a cosine of 0?
1.
What's negative 1 plus 1?
0.
Now, how do we check on this again? How do we check on this again? It's fun. Can you do it? It's kind of fun. You know, hey, I could have made an error there, right? Can't check indefinite integrals, but I can check what? Any definite integral. So let's do it. I go to y equals, right?
Mm-hmm.
What function do I have to type in here?
Sin x.
Sin x, put the original. So you might be like, everyone, I recommend being in radio mode. So I recommend being in radio mode with this. So we can put it in radio mode. Alright, go to y equals, put the sine of x. I'll let you see this. Now, I hit graph, right? And the thing goes squiggling all over the place. Zoom 6 does a standard window. Where can I go? Second trace, right?
Mm-hmm.
Everyone go to second trace. And which one is it?
6, right?
Number 7, correct?
Number 7.
Number 7, it says lower limit, what do I punch?
0.
0, hit enter. That says upper limit, what do I hit?
2 pi.
Hit 2 and then hit pi, and then hit enter, and my calculus is 0. I want to make sure yours does the same, does it? Unless, let me know, Art, if it does one of those 1e negative
No,
3
0.
2s or something. Does it work? So we get the area from 0 to pi, and what's going to happen? Pause it, boom. This is everyone, don't think like, wow, this is going to help me cheat on it. No, it's a learning tool. It helps you see it and you go, yeah, that's 0. Is it working? I'm going to come both of you real quick. Let me see it. I love it. Look at that. You got it. Integral 0, just like we thought. Right? I'm going to go to yours. Did it work? Did it work? I'll go to 1. I'm gonna look at this. That looks good. I'm gonna go to your mode. You're in rating. I like it. And I'm gonna go graph. It probably didn't go far enough, so I'm at zoom 6. Zoom 6 gives a standard window. That's probably why it went outside the window. That's far enough. So now we can go, it probably didn't go far enough. The 2 pi was too far out. I bet you that's what the problem was. And then we try it, now it's gonna work. All right, here we go, number 7, right? 0! And then 2 pi. Ta-da! Isn't that cool? Hey, can we do another? This time, everyone. I want that. So what changes now? What changes in this image?
0 to pi.
Who could predict the answer? I always want you to think graphically. Is this answer positive or negative?
Positive.
See how smart you, oh, you're awesome. You're like, I know this answer is positive. Because you have knowledge of the function. Now, if it's some bizarre function after that integral symbol, yeah, we might not have knowledge, but, you know, we know x squared, we know x cubed, we know these common functions, sine of x, cosine of x, right? Let's try it. So negative cos, 0 and what?
Pi.
Negative cos of pi. Don't forget subtraction. Negative cos of 0. Hey, what's cos of pi?
Negative 1.
All right, what's a negative negative 1?
Plus 1.
Is that 1?
Mm-hmm.
Yeah.
So, if you're doing it on your calculator, you shouldn't put the negative sign and then cos. You should just take the cos and then add the negative sign to it.
That'll work.
Okay.
Hey, what's a negative times a negative?
Positive. Cos 0 is
So
1.
what's a 1 plus a 1?
2.
Isn't that cool? What's the area of that region right there? A perfect what? It's not an irrational number. The area is what?
2.
Exactly 2. I think that's cool. Do you? I think that's cool when you got this function, sine of x, but the area inside that region right there is perfectly 2. Perfect 2. Isn't that cool? Man, you're good. I think you got these trig functions down. Can I erase this image? All right. Hey, is this called a definite integral or an indefinite integral? Definite integral. So we should get a definite value, right? Hey, what would you do if this was the question? How would you leave the answer?
We have to add
Make
the
sure you're
shade.
going that way, right? Make sure you're going that way. What would it be?
Sine.
Sine of x, and then what would I have to write?
Plus c.
Right? I need you to do this. Now, I'm looking around at the faces. I'm trying to read your minds. I was wondering which student was doing this graph in their head so they could predict the answer. Who knows about the Art's doing it? Anybody else? What's the cosine curve do? What's it kind of look like?
Starts at
1.
I'm not saying you have to do it every time, but boy does it help sometimes. You're like, wait, this graph starts here, gets to there at pi over 2, and then it gets where? What do you all think the answer to this guy's gonna be?
0.
All right, let's see. All right, sine of x. Da-da-da. I don't have to put the plus c. Put my pi. Put my 0. Everyone's sine of pi is 0. Sine of 0 is 0. Just like we thought. What we're getting. 0. Cool. Yeah. All right. Don't let the next one stump you. Don't let the next one stump you. We better put some notes over here. This could make someone go crazy on a test or a final. They'd be trying all these like, what do I gotta do? Quotient rule, product rule, whatever. Let me just go over here, a little reminder. We got the s and the c's. And what was the derivative of tangent?
Sine over cosine.
I mean the derivative
Oh.
with respect to x? Secant squared, right?
Mm-hmm.
Okay. Don't forget about that. And who's the other popular one? What's the derivative of secant?
Secant x tan x.
All right. Because I'm telling you, don't ever let these escape your mind. I know the cotangent and the cosecant don't come up as often, but boy, you might stare at this is the problem where you go, man, I would have finished that test an hour ago, but this problem stumped me.
How do you do a secant of something on the calculator?
1 over cosine. 1 over cosine. Zero to pi over 3.
All right. Hey, Owen, this is actually, would you do me a favor? Would you make that pi over 6? You know why? I'm gonna write this. Owen, you gotta give me the exact value. Keep in mind, that calculator doesn't give exact values, does it?
No.
Right? Well, hey, I need a little triangle here. We all know this triangle from the trig sheet. 1, 2, and what? Square root of 3, right?
Yeah, root 3 over
And
2.
there's 60 degrees, and there's
30.
30 degrees. But the most important part to this problem, and when I'm being honest, you could stare at this for like 30 minutes. And you'll be sitting there going, what do I have to do, product rule? Is there a product rule for integrals? And you're freaking out when all along you're like, hold up. What's the integral of secant tan? Secant, you follow me? Same thing happens with secant squared. You look there, you look at integral of secant squared, you're like, what's the integral of secant squared? It's tangent x, right? Alright, so this is just now becoming what? Secant of x. I don't have to put the plus c. Now what numbers do I have to substitute?
5 or 6.
And it's not as bad as you think. Secant's reciprocal, buddy, is cosine.
Mm-hmm.
And when the cosine of 0 is 1, so let's start with the easy one. What's 1 over 1?
1.
Easy. Let me do it again. Secant's reciprocal, buddy, is cosine. Cosine of 0 is 1, so 1 over 1 will just be what? 1. To do this, so katoa, cosine of pi over 6, check it out, is adjacent over hypotenuse. So when I gotta do the reciprocal of that, what's the reciprocal of square root of 3 over 2?
2 over root 3.
That's exact.
Wait, go back over that.
Oh, I'll do it again. It's just, hey, Josie, it's only that little triangle. As long as I know that triangle right there from that trig sheet, and now cosine, remember, cosine is SOHCAHTOA. SOHCAHTOA. Cosine is, here's the angle. There's the angle. I got to do adjacent over hypotenuse. See, adjacent over hypotenuse.
What are the angles in there?
That's a pi over 6, that's a pi over 3. And I just have to do the reciprocal then. And the reciprocal becomes 2 over square root of 3. So it's just the trigonometry. Now everyone, that's fine for a test. You don't have to rationalize the denominator for me. But who would like to rationalize the denominator if you wanted to? I'll bet you the back of the book would. 2 square root of 3 over what?
So 3, sorry, square root of 3 over 2 divided by 3.
That would be 2 times the square root of 3 over 3 minus 1. But everyone, I can't write this more exact. So if you had a high-powered calculator in here, that's how I'd write it. Or it would write it as 2 square root of 3 minus 3 over 1. So I'm going to write that. Some students, they've been schooled all along, always rationalize denominators, so they might write it like that. You know? Like my teachers. Always got to rationalize the denominator, right? Good deal. Any questions on that one? Let's try another one. Ready? How about enough with the trig functions? 6x cubed plus 2x. Let's go from 1 to 4. Cool. What's this become?
X to the power 4.
Can you find my error? And when it happens on tests, be careful.
Yeah.
You know, you leave the room, you get in your car and you're driving away and you're like, oh my gosh, did I take a derivative by accident? What's wrong with that?
That's the,
Whoops, I went derivative of this, I need antiderivative, what is it?
4 divided by 4.
Can you make reduce to 6/4 to what?
Yeah, 3 halves.
How about 2x?
X squared.
Do I have to put the plus c's?
No.
No.
Good. Now what am I substituting first?
4.
Substituting 4, right?
Mm-hmm.
Then I'm gonna substitute a 1. And what am I gonna do with these? Subtract.
Professor, why don't you make the 3 halves?
I'm gonna do that. I'm gonna make this 3 halves. I do. Art, I agree with you. You say, hey, make that neater before we substitute these. All right, put in 4 in there. What do you get?
3 over 2 times 40 over 4 plus 4.
I'm gonna do this. Look. I gotta get that number right there. Then I have to subtract. And then what am I putting in there? What am I substituting?
1.
Yeah, but I want that's 4 to the 4th. 4 cubed is 64 times another 4 is what? 256?
Yeah, 256.
Now what's 256 divide 2?
128.
Oh, why don't you use your calculator to support you here? 128. Now what's 128 times 3?
So that's 300. About 28 times 3 is how much? 72. 128 times 3. 384. Sorry.
384.
Mm-hmm.
Now what's this number right there?
16.
Now what's, oh, we get a fraction. What's 3 halves times 1 to the 4th?
3 half plus 1.
So what I'm doing, there we go. I bet you a lot of you would check this during your test, wouldn't you, with your calculator? Not a bad idea, right? I could mess up that fraction, couldn't I? I could have messed up 4 to the 4th, true? Right? All right. Oh, and what's 390, is that a 400?
Yeah.
What's 400 subtract 2.5?
397.5.
397.5.
5.
That okay there?
If you could possibly do one that uses the first one, the very first equation at the top.
Oh, that was the theory behind all this. That was with Riemann sums. So we don't have to do that anymore.
That we did it the other day.
Yeah, that was just the idea of where it came from. Remember we started with building all those rectangles last class? What we had, oh, we were off. We were what? Estimating, true? Then we thought, theoretically, what if we built what? An infinite amount of rectangles. This is what it turns into. And that built us to here. So that's called the definite integral and led us right to here. So that's what that is, right? That's more what? The theoretical statement, what it's coming to. Ah, yeah. Sum an infinite amount of rectangles. Set it to infinity and you get it. Hey, can I erase? All right, I went tough one.
All right.
What were all those rules for derivatives? What were all those rules for derivatives?
Product, chain.
Remember those? Have we had any yet for this?
No.
Oh, I mean, the only rule we're doing is what? The opposite of the power rule, true?
Mhm.
You go, well, are we going to hit any rules? I'll be honest with you, we hit one rule. But we don't get to it until the last section. We'll talk about it tomorrow. Okay? We'll talk about it tomorrow. So, if we got no rules, now this time everyone, I'm not putting limits on here. So, is this going to be an indefinite or definite?
Indefinite.
You want to look at my back? Look. Evaluate the indefinite integral. You'll see some of these, I made sure to select some of these from the textbook problems, okay? 5x to the 6th. give it a shot. That's a dx off there. Josephine, don't forget at the end we're putting a plus C, right? Now,
Done.
look. This can freak you out during a test. Because you're thinking, what, quotient rule? That was for derivatives. And this is integrals, right? This is integrals, and all we know is what? We can take this x squared and make it like x cubed over 3, true?
Mhm.
So how, and who's got a way to get around this problem? Who's got an idea?
You can like, make it simpler and just cross out the x's.
What do you mean, what do you want to? This is
5x
bugging me, this whole gigantic complex fraction.
5x cubed minus 3 over x squared.
Yes, everyone, he's splitting up the fraction. That's what he's doing. He's splitting this into two separate fractions. He's saying, look at this as 5x to the 6th over x squared minus,
3 over x.
all right, outstanding. If we didn't do that, I'll tell you what, we've been staring at this for hours. We've been going, quotient rule, or, opposite, what's the opposite of a quotient rule? And we were trying to figure it out. That's gonna do it. We had to split this into two. Now, if you're curious, like, well, what happens when there's like a binomial down here? That's coming up. That will come up later. So, can you help me simplify that? What is it?
Yeah. 5x cubed over 4.
Now, be careful here.
3 to the x cubed power minus 2.
X to a negative
2.
2. Don't agree? Now, when I still haven't done the integral yet, so I gotta keep the what?
dx.
Dx. Cal, you okay with that?
Yeah, yeah.
Now, let me tell you something. Heads up, everyone. I get it all the time. Class size of 25 Calc students. Sometimes up to 10 students will tell me the integral of this is negative 3 ln of x squared.
No.
Be careful. What's the only one that becomes the ln of x?
1 over
You
x.
remember? Only this guy, right?
Mm-hmm.
I'm gonna agree is natural log of x plus c. Don't forget that. So is this a natural log right there? No. But I think after this I should do one, so one sees the difference. Alright, this will be easy. What's the integral of 5x to the 4th?
X to the power 5
Good deal. What happens to those 5s?
cancels out. Then
-2. Everyone be careful.
negative 1.
Be careful. You gotta raise -2 by how much?
1.
Sometimes people, it's a number line thing. What's -2 plus 1 in math? Not -3, but,
Negative,
and then I gotta divide by that number.
negative 1.
There you go. Be careful. That's another common error. People accidentally do -3 over -3. It happens. Oh, don't forget I have to put the plus what?
Plus c.
I have to put this y. Plus constant, antiderivative. Now, and we should definitely simplify that. Could you tell me this in a nice simplified manner? X to the 5th.
Plus,
That minus and that minus means the what?
plus,
That 3 is up top. And where can I move an x to the -1?
below.
That's the best way to write it. If you want to combine these fractions, you can, but I would just leave it like this. That puts a smile on my face. You got it. You had to substitute 1s or 2s or 3s, you'd be okay right there, right? Yeah? Now I want to wait till everyone has this, and we're going to change that bottom to an x. Because then you get to an ln x, right? Then the natural log comes up. Great job with this. Everyone okay with that? Yeah? Yeah? Alright, here it comes. I just want to know the answer. Well, what happens here?
That will be 3 natural log of x.
I'll just write that again. Let me wipe that out.
3.
How does this work? The 3 is the constant,
Mhm.
but we know the integral of any 1 over x becomes what?
Wouldn't it be 5x to the 6th over x, not x squared?
5x to the 6th over
Oh yeah,
x.
5. It will be 5. Yeah, she's right.
I gotcha. And so this would be what right here?
X over 5. Yeah.
And this would become a
5.
5. And I'll put this right down. Good. Josephine, what would this be? 5x to the 6 over.
Six.
Now, how about this guy?
So
The
should we-
3, let it sit there like a constant.
Mhm.
But what's the antiderivative of 1 over x?
Natural log.
Natural log, and what do I gotta put on
Absolute
this?
value.
Yeah, put a little absolute value bar around it. You know, what's that for? Well, you can't get the absolute, you can't take natural log of negative numbers, right?
Do you have to give that like for this x then, or do you have to give it the thing like when from negative infinity to 0 union 0 to infinity?
Nope, you wouldn't have to write that.
Okay.
Good question. Good, I got you, because you're like element 0 is undefined.
Yeah, exactly.
Very good. You're gonna like Calc too, because you do something called improper integrals.
Uh-huh.
And people do stuff like that. They go, da-da-da, da-da-da, and then they go to, like, stuff like this. And when that's Calc 2. And you're like, wait a minute, what's the natural log, what is that number?
0
You go, what's the natural log of 0?
undefined.
Undefined, but when you think of this graph, look at it. It goes like this, right?
Uh-huh.
And the idea of calculus is maybe the area in there converges to a number. Isn't that cool? That's the idea. It's called, don't worry, it's not in our course, but it's called improper integrals. And you got to think about it. You go, yeah, maybe the area in here what? It gets so tight so quickly, maybe it converges, and there you get the limits again. And so you go, oh, it's like a limit approach into that.
There's like something like Taylor and Maclaurin series, something like that.
And that's right after that.
Okay.
That leads to the Maclaurin series, that's
Yeah.
right. But isn't that cool? And so I just want to point out, sometimes they call them improper integrals. So everyone, by accident, I might be up here just making up problems. Somebody may catch me and go, whoa, 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 professor, that's an improper integral. Because I can make sure I don't do something like that. You know, put an integral over like an asymptote or something. You follow me? Like, I can't have you do this today, look. Everyone, let's do 8 over x squared, right? And I go from negative 2 to 3. I can't do that. You know why? This function, what's going on at 0? It's undefined. This function has an asymptote at what? It's got a vertical asymptote at x equals 0. I just broke right through the middle of it. It's called an improper integral. So if I accidentally write one of those, someone can call me on that, okay? All right, I'm going to finish this up. That became this. This became that. Is everyone okay with that answer?
Mhm.
Is everyone okay with that? Yeah? But be careful. What if this was 3 over x squared? No natural log, right? Good. Hey, speaking of these, I always get a kick out of this. Look. You go from like 2 to 3. And you got to find this integral. Well, what's the integral of 1 over x?
Natural log of x, but you
With
have
the
to
bars.
plus
You got to put a 3 and a what?
2.
There are only, there's only like 3 log properties. I always get a kick out of this. My students are so afraid to use those log properties. They leave their answer like this. Do you remember log properties? Another way you
You
can write
can
that?
divide them.
Did you know this? This is a property of log, that you could write it like that. I just want to point that out. Keep in mind those log properties. I can write this like this.
Will we get it wrong?
It's got a property of log. See, I knew
No,
that was coming up.
No, you're
I
not
knew that was
going
coming.
wrong, but you can write it.
It's good to do that. And Bill Reg, I'll be honest, my midshipmen, they'll never do it. You know, they'll always leave it like what? Natural 3 minus natural log of 2. But I want to point out, there's not like there's 50 log properties. There's only these what? 3 simple log properties, and this is one you can always do that. Cool? So I want to point that out. Plus, I think it's good to do that because you might check the back of the book and go, I got this. How did they do that? You go log properties. Okay? Good deal. All right. And when here comes another special case. Special functions. You got trig functions down, right? I give you a polynomial, you smash that. I give you that, they call that a rational. I had a rational function up there, you crush that. How about this guy? There's 2 ways to do this. Evaluate the indefinite integral. Give it a star. What's special about it? Come on, there's something
So
special
we have
about
to
it.
find the
Do you see
critical.
what I got there around that x plus 2?
Yeah,
What are those?
absolutely.
Absolute value bars. So there's 2 ways to do this. One of them is algebraic approach. Another approach is geometric approach. You know why? Everyone, the absolute value function. The absolute value function. What does the function look like in an image? a what? A V. And think about that. I want you to think geometrically like, oh, I can make little triangles, right? So we're going to do this problem two ways. I
No.
think on a test, I'm going to give you the option. Does that sound cool? Does that sound fair?
Uh-huh.
I'll say, you got to show me this geometrically or you got to show it to me algebraically. And we'll do it both ways.
This is just a random question, but on the interval itself, does the lower value number always go on the bottom, or does it really matter?
Yep, it always does. Now, did you see what I did here? That was a Professor Messenger error. I meant to put what here?
-2.
Well, I actually meant to do this. Okay?
Right.
But I gotta answer that.
So
The
the lower
professor.
value number does always go on the bottom?
Let me write it down, and we're gonna do that problem. Thanks for spotting that. Now, what did I have originally? And I'm gonna write this, we'll talk about, what did I have originally?
4,
Negative 2 on top of
4 and -2.
So I'll make up, well, I'll just make up some bizarre, weird ones, but I'll put this number higher, like 8, and -3. So if you ever get a problem like this, the very first thing I want you to do is switch these so the lower number's here, and then what do you gotta put in front? Tell me.
Negative.
Put the negative. So that's what I want you to do. So Josephine, you ever get this? Anybody in this class, you ever get this? Right away go, I'm gonna put a negative down, because we always wanna think lower limit, lower value, upper limit, upper value.
Now, professor,
Cool?
however, you can do it in that way too, like 8 and 3, but you have to take negative x over it because -2 is a cut point, and -3 is
That's
left.
right.
Right. you can
That's
do that.
exactly right. So that's a good habit in it, and I'll be honest, I didn't mean to do that. I wrote it that way. But it's good to think that way, right? So if anybody ever does that, you can go, oh, this is equivalent to this. And then you can rock and roll. Cool? Alright, now. Let's do this two ways, but on a test, you're gonna pick your what? Your favorite way. Now, let's start with the geometric approach. What does that mean? Oh, you and I are doing what? Geometry? We're drawing a graph. Now, who has knowledge of this v function? It's shifted 2 notches, that way or this way?
So
If you just set that
left,
equal to 0, you'll know.
left to the left.
Good deal. Goes to the left too?
Mm-hmm.
But we gotta make a really nice graph, okay? So you said it went left too?
Mm-hmm.
Okay. There it is. Now let's plug some numbers in here. What's going on with this function at like -3? Because you gotta go from -4 all the way to what?
2.
So let's make a really nice sketch. You're telling me this function's gonna hit right here, right?
Mm-hmm.
Now I want to just tell me what's, what you plug an -3 in there, it's a what? It's a 1. How high does it get at 4? How high does that get? Does it get up to 2? Alright, how high does it get at 1? How high does it get at 2? Alright. And am I making the graph correctly? But how far do I gotta go out to with this graph? I gotta keep going all the way out to what?
2.
Now who can tell me how high does that get at 2?
4.
So at 2 it gets up to 4, does everyone agree? Just plug a 2 in there. And we just plug a -4 in there, it's 2, right? Now, what's this integral? Oh, I see 2 triangles, do you? You all see 2 triangles?
Mm-hmm.
Here, I'm gonna shade them. Finds area under function. This function's not going underneath the x-axis. Everyone, I need a half base height on that dude, and then I need a half base height on this dude. Just be careful, okay? Just be careful. What's that base right there?
-2 to 4 is -2.
That base length is 2. What's that height right there?
What is that? 4. 4 is what? 2?
2 times 2 is 4. What's half of 4?
2.
Is it 2? So can I put a 2 in here? Can I?
Yeah.
Okay, what's that area? Be careful. Look at that base. Look how far it is. How far is it?
-2 to 2. So that's 4.
4? 1/2 of 4 times 4. What's that area? I went from here to here. What's this entire area? 8? Zone agree? So what's the entire integral? It never went underneath the x-axis, so we're going to do what with these? We add them. We don't subtract these areas. Do you all agree? Some students get freaked out though, they go, yeah, but it went on the left side of the x-axis. Who cares? And only reassign negative values to the area if it goes underneath the x-axis. So what's that area plus that area?
10.
And I say, hey, you gotta show me your work. You're like, right here. Right? I think geometrically is easier here. Now, who thinks they know how to track this algebraically? Because it's gonna be a lot more work. What do I gotta do?
So, it's from 0 to 2, you have to do x plus 2, and then -4 to 0, it's negative x
Oh, he nailed it, Emily. You know what he's doing? He's making it a piecewise function.
Yeah.
That's the only way we can attack this algebraically. I want to point that out. What he's doing is he's removing the bars. But if you do that, the only way you can remove these bars, all right, is if you talk about these two separate functions. So let me go in here and label these. You know what that function right there is? That is y equal to x plus 2. Nice! From here to here. But what is the function from here to here?
Negative
Nobody
x
write
minus.
the exact thing, but put a negative around it. So from here to here, look. Negative outside, that's what he's saying. Okay, go ahead.
Could you just plug in like -4 plus 2 and then just take the absolute value of that?
I wish. I know, I wish it was that easy, it isn't. You know why? I want you to believe me. When we're done, we're gonna check this on a calculator, and I want you to see the delay in the calculator. You're gonna get like this delay. It's gonna be like, it's gonna take a while to get the answer. Because it has to run through a program to find out where it hit this what? This x-axis and stuff. So and this is the only way I can do this, what? Algebraically, ready? Here it is. I gotta do an integral from -4 to what value? It's important. Which value?
2.
Yup, to this -2. And which function is it? Is it x plus 2 or negative x plus 2?
Ne-
Put a negative outside those parentheses. dx.
Why'd you put a -2?
That's the point.
From
of
-4 to -2, I'm gonna use that function. And look, Josephine, I have to put a minus outside the entire what? X plus 2. So I can distribute that minus, right? I can do all that math right there. A lot of negatives in there, do you agree? Then I have to add it to, what's the next interval?
-2 to 2.
Now you're gonna write it from -2 all the way out to what? To 2.
2.
And which function do I use here?
X plus 2.
This is, hey Josephine, if there was a quicker way, I would do it with you, you know? If I had a choice on a test, I'm going geometrically. A couple triangles, right? Come on, you can't beat that. A couple triangles. Half base side, half base side. Here. This is can I say it? Tedious? This is going to be tedious. Watch. And what's the integral of -x? Ugh, you get -x squared over 2.
2
Right? What's the integral of -2?
minus 2x.
Now what do I got to plug in here? And there's a lot of minuses in there. Could I make an algebraic area? That's a minus, by the way. Then I got to do the plus. And what do I got to do here?
X squared plus 2.
I'm already tired. You follow me? Look at all the math I have to do. You want to see it all written out? There we go. It's going to be a lot of parentheses. Look. You got to be careful with all these what? Woo! See this? I don't feel like doing all this. Then I got to subtract and do what?
Plug in the 4.
Negative.
Negative 4.
-4 squared over 2. Let's see all that? That's half the work. Now I gotta do what? That was this part. Now I have to do plus. But hey, some students go, I don't mind. Minus, and then the what? And be careful with -2s, okay? I'm not going to finish that out, but everyone, what will all that math come out to be? Come on, we know. What's it all going to come out to be again? 10. Does everyone see all this mess? That minus that plus that minus that would give me the 10. Right? This first half, what would be the value from this first half? Look at the image. What would be the value from this entire first part right there? All this would be what number? 2. Cal, do you see something?
Yeah, in the second parentheses, no.
You okay?
Negative 2 minus 4, shouldn't that be a plus? Or am I
So
looking
that's
at
a
something?
plus?
No, when you wrote it out. Keep going. No, the other, to your left. No, before that. There. Shouldn't that be a plus 2, or am I looking at it wrong?
No, minus 2.
See, all I had to do was substitute -4 for that x into that one. So I'll substitute -2 in for x, substitute -2 in for x.
Yeah,
Then a subtraction.
yeah.
Then I have to substitute -4 in for x.
Oh, I'm sorry, I thought you were working with the
And
other
then
side.
negative 4
I thought
for
you were
that.
working at the other side, I'm sorry.
Yep, I'll branch off this wall. But boy, doesn't it get tedious?
Okay.
Mm-hmm.
It's not like it's crazy, but I do want to point out this left side would turn into what number? So you can
10.
see it. What value would it be? 2. Well, this part, from -4 to -2, all that math right there, Kel, would have to be the
2.
number 2. We can see it.
I thought you didn't combine them already.
I got you. And then this part over here, all this junk, this part coming from this, will turn out to be the 8. And what's the 2 plus the 8 going to be?
10.
10. Now, on a test, I'm giving you an option. You can do what? Geometrically? No, I would take the which approach. But if you freak out on the graph and stuff, do the algebraic approach. Just take your time. A lot of negatives in there, right? Now, I want to show this to you. Would you try sending a calculator? You're going to get a delay. Would y'all try it? Where's the apps button again? Catalog? Yep, go to catalog. Try it. I want you to see. You get over the delay. Oh, you already did it. Did you do it?
Yeah.
And you second what? Cal?
7.
7, hit it. Did you see this delay? Or go from -2. Oh wait, just pipe in a number. Negative, where are we going from? -4, then upper limit, what's the upper limit? Grab. Upper limit. See the delay? See the delay?
No,
Isn't that cool?
mine
Now,
would-
you know what his calculator did? He's got a TI-83, it had delay, and it went 10.000381. We know the exact answer, what is it?
10.
Isn't that neat? You know, $100 tool here, and it still can't give the what? Exact answer, isn't that neat?
Mine just didn't go
Oh, yours is quick? Well, what's up with the 381, huh? We know it's exactly what? Now, don't you love that? I know. The people make sense of those funny numbers are all the computer programmers in this class. Anybody in that field of computer science, computer sci people? Yeah. You get the sense of why that thing has that round off here at the end. Did it work?
No.
I'll show it to you. Yeah, only take a second. We just gotta find that apps thing. So, ooh, nice graph. And then you go to second calc. I'm gonna go to number 7, right? Lower limit, -4. Upper limit, 2. 10.381 or something like that, but it's 10. Is that together?
So you have a rational function on both numerator and denominator are apps. Then
right.
then what will you do?
I gotcha. So you're gonna still have to do, if you got apps in both parts, you're gonna have to still break up a piecewise function.
Piecewise function and do it.
You will. I don't think you'll see any of those, but that's what you do. You're like, I gotta do a piecewise.
Professor Mazur used to let us do that.
Did you really? She liked to do after
They
the
she
out.
love. That was a favorite thing.
Aaron, if you took pre-calc here, do you remember he's talking about there's like this absolute value supplement that the math department made up? Yeah, and you can do all these different things. That's the idea of just doing these piecewise functions. But does that one make sense of why this is x plus 2 and this was negative x plus 2? Does that make sense? Yeah? Alright, hey, good job with that. Seriously, doing a really good job. Two more problems right here. This is the first one. I want to make sure you're clear on this. He said we don't really need that, huh? That was just the what? That was just the theory. We understand the concept of where this is coming from, right? Theoretically, Riemann sums. But how many rectangles? How many, what's that symbol? Infinity, right? Okay. So on 2 problems, here's the first one. It says, this is in 5.3. It says, can you use part 1 of the fundamental theorem of calculus?
Which one?
This is number 7 on page 394.
Okay.
Can you use part 1 of the fundamental theorem of calculus to find, listen to this, ready? Find the derivative of this function. So I hope this takes you like 1 minute. We can spend the last 3 minutes on a tougher one. Did anybody want the page number on this?
394.
Then go find the derivative. And can you find g out of x? I'm hoping it takes you like 2 seconds.
1 over x cubed.
G is the integral from 1 to x, 1 over t cubed plus 1 dt. Then what's g prime of x?
1 over x cubed.
I love it. No tricks, right? Cool. So what's the last problem? Didn't you love that? And the last problem is a preview of the substitution rule. Okay? Oh, I'm sorry, this is called the integral net change theorem. The last thing when I want to get to 5.4. This is my last problem, but do you recall this? Ready? What happened with this function right here when we went from 0 to 2 pi? Do you recall?
0, right?
It equaled 0. So, and you know what we're saying? What we're saying is, why did that become 0? Because this area was signed what?
Positive.
Positive. And this area in here was what?
Negative.
Negative. Positive, negative, 0. So, if I ask you to find this, and I call this velocity, then in calculus and in physics, integrals are called displacement. If you go from some a value to some b value. So for the last problem today, and let's just say you got a function, and it goes like this. It gets up to 6 at 2, flat lines, then at 8 it comes back down, and it gets down to, and how about I go at 10, let's say it gets to negative 4. So Kel, I want to make sure I've got this lined up right here with a y value of negative 4. Last time was off a little bit. Everyone, in your image, when you put this in your notes, what's this value right there?
Negative 4.
Negative 4. Everyone got that? Look okay. Let me make sure that reaches our negative 3, 2, 1. This one's 1, 2, 3, 4, 5, 6. Not drawing the scale, but this got down to a what? Negative 4? And I'm going to call this function v of t. This is t, this is time. This is the velocity of a bug, okay? Now when the bug is crawling along this edge right here, it's just crawling along this edge. When it goes to the right, positive velocity. But guess what happens? Sometimes the bug turns around and goes this way. That's called negative velocity, right? You go, why? Because it's going in the opposite direction. Same thing can happen with this chalk. I throw this chalk up in the air. When it was going up, it had what? Positive velocity. When the chalk was coming down, it had what?
Negative.
Negative velocity. Now, who in this class knows that this specific instant, when this got to the highest point, the velocity of that chalk?
0.
0. There was one moment, right? Same thing with Zan. Zan may crawl to the right and crawl to the left, but when it turns around and crawl left, you know what its velocity is going to be?
0.
0. So hey, just to give me, before I do this problem, this, kind of like the sine curve, this is the velocity of me. Ready? Alright, 1, 2, this is going to be in seconds. I just want to give you an example, right? Here's me. Start the clock. Go! 1,000, 2,000, 3,000, 4,000, 5,000, but I should do right and left. So right's going to be positive, left's gonna be negative. So let me start right here, ready? That's gonna be velocity of me, go! 1,000, 2,000, 3,000, 4,000, 5,000, 6,000. So, can you tell me, what should this answer be if I do the integral of this
Zero.
function right here? And the integral of this function, we can tell would be what?
0.
So what are we really finding? Not my total distance, but my what?
The net velocity.
Displacement. And they call that displacement. How far from my original position am I? I started here, where'd I stop? Right here.
Yeah.
So my displacement is what?
0.
0. Do you follow me? Good. So when that's what integrals find, it finds displacement. So now, I want you to find this right here, and I want you to go from 0 to 10. And what do? I know what you do. You take all the areas, and then you what? What's that area?
2 times 6, 12, 6. So that's the first one is 6.
And we'll be done in 1 minute. I just want to put this down too. Okay. And when I gotta get this area, half of 2 times 6 is 6. What's the area of this rectangle? 4 times 6 is 24. What's the area of that
24.
rectangle? 2
6,
times 6 is
12.
12, take half of that, so I get 6 plus 24 plus 6, but I gotta subtract out this area, right?
Uh-huh.
Displacement, and what's the area of this? 2 times negative 4 is,
Negative 8.
what's
divided
half of negative 8?
by Negative
I'm
4.
gonna put a negative on it. Now what's that all out to be?
36 minus 4, 32.
Is that 32?
Yep.
So when I'm getting 32, I wanna make sure everyone sees why, because it was the 6 plus the 24 plus the 6, and then we'd have to subtract out the what?
Negative 4.
4. And for the last problem today, everyone, I want us to find the total distance. So think about me when I was traveling here. That would be like adding this to what? This. So if you want to find the total distance, this is what you find mathematically. You got to find the integral to what? The absolute value function. Now what's the absolute value of a function do? You all know. What would it look like? Total distance would be, take the 6 plus the 24 plus the 6, but help me out. You wouldn't keep this negative, what would you do?
Positive.
You would add the 4. Because you're saying, what's the total distance? You would add what's underneath this because that function we get like that. Does that make sense?
Uh-huh.
So for total distance, we add any area that's underneath. So what would be total distance?
40.
That would be 40. That would be the total distance. So what was the total distance that ant traveled? Hang on, let me move these chairs out of the way. Ready? What did that ant do? That ant went to the what? During the first 8 seconds, it went like this. When did the ant turn around? At t equal to what? At t equal to 8, the ant turned around, then he went which way? It went back a little bit, right? But if you had to take this distance, add that distance, we just add that last what? 4. Does that make sense? But displacement is integral. When you put absolute values on the function,
It becomes distance.
it gives you the total distance. Sound cool? Everyone have a great one.